All right, so last time we looked at some different formulas associated with right triangles. We looked at the Pythagorean theorem, and we looked at the abbreviation SOHCAHTOA and talked about what those each meant. And we're going to look at a couple other things today. The first idea that we're going to talk about, and you've seen this used before, is what an identity is. So an identity is simply an equation. It's not specific to trig. Any equation that holds true for any value of the variable in the domain. And just to show you that it really doesn't mean that it's only trig stuff, you've seen them before, and here's an example of one. If I have the equation 2 times x plus 3 equals 2x plus 6, that's an identity. Right? If I simplify the left-hand side by distributing, it would look exactly like the right-hand side. That means x could be any value, and this equation would be true. And that's all it means for it to be an identity. Okay? Reciprocal. What's a reciprocal? Okay, it's not a negative opposite. And what do you mean by opposite? What's flipped? A fraction. So we tend to talk about reciprocals when we talk about fractions, right? So if you take a fraction or something that is written in fractional form and you flip it upside down, that's what we call a reciprocal. Another description for a reciprocal is what we call a multiplicative identity. In other words, it's the value we would multiply and get us back to the number 1. All right? So this is the multiplicative inverse. Of a fraction a over b, that is a over b and b over a are reciprocals. So as this relates to trig, we encountered some reciprocals last time. We didn't really use that language, but they were reciprocal identities. And we did them in terms of the opposite and the hypotenuse and the adjacent sides of a triangle. And we kind of put them together in pairs. The sine and the cosecant went together. The cosine and the secant, they kind of go together. And then tangent and cotangent, they go together. And they go together in this reciprocal identity sort of relationship. So the sine of theta is exactly the reciprocal of cosecant. So I could actually write sine of theta as 1 over cosecant. And there may be occasions, and in fact there will, that we want to do that. The same thing for cosecant. I can write it as 1 over sine of theta. Now make sure every time you're writing a trig identity, or trig name, sine, cosine, and so forth, the trig function, that you put the angle after it. That theta is important. It doesn't mean anything without that value after it. It would kind of like being able to write square root out in the middle of nowhere. Square root of what? Square root has no meaning except for what's underneath the square root, right? The same thing with these trig functions. They have no meaning apart from the angle that's associated with them. Cosine, it can be written as a reciprocal of secant, and then secant also as a reciprocal of cosine. And then likewise, tangent is the reciprocal of cotangent. And cotangent is reciprocal of tangent. This is a calculator caution more than anything, but it's something to be aware of. There's a button in your calculators that has a little -1 after some of your trig functions. In particular, it usually has it after a sine and a cosine and tangent. This little -1 is not the same as the reciprocal. This is not the same as 1 over sine. Now, at some point in the semester, we will approach what this means. It's not too far off. but that's not the same meaning. Okay, so don't be misled and think that you can use that button to find out what the reciprocal of sine is. You can't. Okay, the reciprocal of sine is cosecant, and the way that we would get that with our calculator is doing 1 divided by sine. Right? I bring this up, and there's a few other identities in this section that we're going to bring up. The quotient identities are in the next one. So the quotient identities are helpful in relating tangent and cotangent to sine, cosine, and so forth. So the tangent can be written as the sine value over the cosine value. And cotangent can be written how then?
Sine over sine.
Right. The reciprocal. So all I have to do is to write the flip of that fraction. And again, these work for all angles in the in the domain. That is, you notice the notation here that says the denominators are not 0. In other words, those locations where cosine or sine actually have 0 as their output value, it's not going to work here because I can't divide by 0. There's also some Pythagorean identities. Now, we did a Pythagorean identity last time, and it was the one that you're most familiar with, and what did it say?
A squared plus b squared is equals c squared.
A squared plus b squared equals c squared. There are 3 forms of Pythagorean identities as they relate to trig functions that are also very helpful to know. The first one is the most helpful. That is, you see it used the most. And it's the identity that says sine squared plus cosine squared of theta on each of those equals 1. And if you remember any of these 3, this is probably the one you remember. Okay? The others relate tangent and cotangent and secant and cosecant together. So the second one is that tangent squared of theta plus 1 equals secant squared of theta. So it doesn't quite have the same form as the first one, right? It's not tangent squared plus secant squared. They're actually on separate sides of this equation. And then the last one relates cotangent. So we take cotangent squared of theta plus 1, and what do you think it equals? Cosecant squared of theta. So these are 3 Pythagorean identities that are helpful to use. Now, I want you to take a look at the next example. Problem 3. Unfortunately, it's been 2 days, but we did problem 3 last time. And when we did problem 3 last time, we did it with triangles. Do you remember doing that? And I created a triangle so that it actually fit the description that secant of theta is equal to 3, and we found the opposite and the hypotenuse and the adjacent sides, and we went from there. Okay? That is not the only way of doing this problem. So I want to show you another way of doing the problem. In the grand scheme of things, I don't care which way you do the problem, but you will probably have a natural inclination to do it one way or the other. And so I want you to be aware that there's 2 options. All right, so this one says, use identities to find the values of the remaining 5 trig functions of the acute angle theta. Now, finding cosine, it's not any different. If the secant of theta is 3, what's the cosine of theta? 1 over 3. It's a reciprocal, and in fact, you used the reciprocal identity to do that, which is one of the 3 sets of identities we just talked about. Now, the other options do not include drawing a triangle in this case. Okay, that was the method we did last time. What we want to do is we want to employ the different trig functions, identities, that we just talked about. So we have quotient identity, we have Pythagorean identities, and we have reciprocal identities. Well, reciprocal identities can't be used any further right now because I already did them. Okay? So we're going to use a Pythagorean identity. In particular, you see secant theta here and you see cosine theta here. What that means is that I could use either the sine squared plus cosine squared equals 1 identity and the cosine value to find sine, or I could use the tangent squared theta plus 1 equals secant squared theta identity and I could find tangent. Or I could use both of them and find each of those items, right? Which one do you want to find first? Do you want to find tangent first or sine first? Sine? Okay, let's find sine. All right, so if we find sine, I need to take the sine squared of theta plus cosine squared of theta. It's supposed to equal 1. So I know what cosine theta is. Now, be careful. I'm not replacing theta. I don't know theta. I know cosine theta. So I'm replacing the entire expression cosine theta with 1/3. And I'm supposed to square it because cosine is supposed to be squared in this formula. So I'm squaring the 1/3 value. That make sense so far? Okay, so somebody's going to tell me what is 1/3 squared?
1/9.
1/9, good. And then I need to get that 1/9 to the other side, which means I will subtract, right? What is 1 minus 1/9? 8/9. That's what sine squared is equal to. How do I find what sine is equal to? Square root, you bet. Very good. Now, for the moment, you're seeing me not sort of, well, you're seeing me ignore a fact. You're seeing me ignore the fact that when we put square roots into a problem, we put a plus or minus on them. We'll address that later. That's not kind of the point in this particular section. So I'll let you know when we get there. But at the moment, we're just going to keep going with this. This gives me the sine of theta on the left. I like the square root of the denominator. It's 3, right? Mm-hmm. We did square root of 8 last time as well. And remember, the way that we do square root of 8 is we simplify it. And we write it as square root of 4 and square root of 2. And the square root of 4 is actually 2. So this is 2 over the square root of 2. Right? So that's sine. Once I have found sine, which one's easy to find next?
Cosecant.
Cosecant. And why is cosecant easy to find, Lauren?
It's just a reciprocal.
Because it's the reciprocal. You got it. So I'm going to take this sine value, and I'm going to do the reciprocal to find cosecant. So let me put it over here, since I have a little bit of space left. So I need the reciprocal of this, which would be 3 then over 2 square root 2. Do I get to leave it that way? No. What am I going to multiply the top and bottom by?
Radical 2.
Radical 2. So what will I actually end up getting?
3 radical 2 over 4.
3 radical 2 over 4. I can't simplify the square root 2 and the 4, just because they both have 2's in them, because one is underneath a radical. Okay, so I've found 3 of the 5 that I'm supposed to find. The last one that I'm supposed to find is the cotangent and the tangent pair, right? So we either can use the cotangent squared plus 1 equals cosecant squared, because I actually know cosecant squared now, I just found it. Or I could use tangent squared plus 1 equals secant squared. I like using tangent a lot better. Why would tangent be easier to do in this problem? Because there's no square root involved in secant, correct? In fact, secant's a beautiful whole number. It's not even a fraction. So it's going to be really good to work with, or clean and easy to work with anyway. All right, so I know that the tangent squared of theta plus 1 is equal to secant squared of theta. All right, so I have tangent squared theta plus 1. Secant is 3, so this should be 3 squared on the right-hand side. So here's tangent squared theta plus 1 equals what? 9. So what does tangent squared equal?
8.
It equals 8. And if I take a square root, it looks like a number I've already taken a square root of just a moment ago. So how do I get to simplify? 2 square roots of 2. So that's my tangent value. If you're not, I'm using a different color. I thought you guys could see the different color. It doesn't look like you can. It's too dark. That's tangent. So cotangent then would be, well, 1 over 2 square roots of 2, right? And when I simplify that, or rationalize that, I get square root 2 over 4. Now make sure when you're doing this for me that you're really clear as to where your solutions are, because I only have so much space on my screen, but you have much more space on your paper. So one of the things that's really helpful for me, instead of hunting through all of your work, is if you'll actually show me the solutions. So this is one of them. This is one of them. Over here is my sine value. I have tangent right here. And then this was my cotangent over here. Okay? Any questions on how we did those? Again, if you don't like that method, you don't have to use it, right? You have two ways of doing this problem. All right, fundamental identities are the three sets of identities we just talked about. So these are comprised of reciprocal identities, quotient identities, and Pythagorean identities. That says identities at the end, or pretend that it does. So when we say fundamental identities, those are the three different sets of identities that we're talking about. I need you to know that because if your question asks you, use the fundamental identities, you need to know what it's talking about. And it's talking about those three different sets. What are complementary angles? Okay, so what do you mean one's that? Two angles specifically. Very good. So these are two angles that add to 90 degrees. And I'm going to insert one other word in here. Right in here. They are two acute angles. In other words, I'm not talking about negative angles here. We don't have 100 and negative 10. Okay? So we actually have two positive numbers that are adding up to 90 when we're talking about this. The Complementary Angles Theorem is the cofunction, it says the following. Cofunctions of complementary angles are equal. And we're going to explicitly say what that means, but this is the general statement, okay? So these are cofunction identities. So these are not fundamental identities, right? This is not one in that list of identities. The cofunction identities, though, say the following. So sine has a cofunction. What is the cofunction of sine? Nope. That's the reciprocal of sine is cosecant.
Oh, sine a negative one.
Nope. It's all in the language. The cofunction of sine is cosine. Yeah. So it's not trying to trick you. Okay, we're not talking about reciprocals. It's the language that we use, right? Sine and cosine. Tangent and cotangent. Secant and cosecant. Are you with me? Okay, so if I have the sine of an angle theta, this is equal to the cosine of the complementary angle. Well, the complement to theta is 90 degrees minus theta. All right, so if theta was 40, then its complement would be 50. Okay, so this is saying that the sine of 40 and the cosine of 50 are equal because they're complementary angles. Likewise, I can write cosine in the exact same way. I can write the sine of 90 degrees minus theta. So tangent will be written how? Same pattern. It's the cotangent, and I don't have enough space. 90 minus theta. How will cosecant be written? Secant of 90 minus theta. How will secant be written? Cosecant of 90 minus theta. And how will cotangent be written? Tangent of 90 minus theta. These are cofunction identities. And we're going to take those cofunction identities and the fundamental identities and take a look at simplifying something that looks horrid. Because I don't know about you, that looks really messy. Does it? Did you have a question?
I'm sorry, can you go back?
You bet.
I think it got flipped around on my paper.
No problem. Did I write something wrong? I might have.
It just, I think like the...
Oh, they're not in the same pattern on your paper as they're on my screen. That is my fault. Absolutely, 100%. I'm sorry about that. I did not get them in the same pattern. Did everybody find the right spot where they were supposed to be? Okay. All right. Am I good to go? Is that all right? Okay. Sorry about that. All right, so we have these fundamental identities. That's reciprocal, Pythagorean, and quotient identities. And then we have these new identities that I just introduced last time, or last slide, which are the cofunction identities. So let's take a look here. Tangent 10 degrees, cotangent 10 degrees. What does that simplify to if you multiply those?
90 degrees.
No, you're thinking about cofunction identities, but I'm not simplifying cofunction identities because tangent and cotangent have another relationship as well. One, tangent and cotangent have this wonderful relationship and they're reciprocals, right? What happens when you multiply reciprocals together? They cancel each other. They cancel to the number 1 specifically, right? So tangent of 10 degrees and cotangent of 10 degrees right here, this is equal to the number 1 because they're reciprocals. It's like having 4 over 5 times 5 over 4. What about this right here in the middle? Cosine squared. Good. So this is a quotient identity, isn't it? Cosine over sine is cotangent. The 25 degree stays. What else stays? The squared. Right? If cosine over sine is cotangent, then cosine squared over sine squared is cotangent squared. How about this last one? 1 over sine squared of 25 degrees. How else could I write that? Cosecant squared. And that's another reciprocal identity, right? Now what? What identities just beckon you to look at them again right now? The Pythagorean ones, and the ones specifically that relate the cotangent and cosecant in some way, shape, or form together. So what could I replace? And there's not just one right answer here, but what do you see that could be replaced? Let's see. It's the last one, isn't it? Cotangent squared plus 1. I could replace all of this piece with what? Cosecant squared of 25 degrees. So what is cosecant squared of 25 degrees minus cosecant squared of 25 degrees? It's 0. So that original expression was just a real fancy way of writing the number 0. Right? I mean, that's what it was. So this one simplifies to 0. Okay, we've got one more. This one says 1 minus cosine squared of 20 degrees minus cosine squared of 70 degrees. Now, there's something very different about this problem than the last problem. Do you notice what it is? The angles aren't the same, right? Take a look back at the last problem. I know I had the 10 degrees up there at the front that were different than the 25s, but those 10 degrees went away really quick with a reciprocal identity. After that, all my angles matched. This one, the angles do not match. But how are the angles related? They're complementary, aren't they? Yes, they are. So I can use those complementary angles with that cofunction set of identities, and I could replace one of them. And it really doesn't matter which one we replace. I'm going to replace the second one just because it's second. How else could I write cosine of 70 degrees? Sine of 20 degrees. And because the cosine was squared, this will be sine squared. Okay, so that's good. My angles match now. That's good because that allows me to use the fundamental identities because those all had matching angles when we were looking at those identities. But if you take a look at this, again, I see lots of squared things. So I'm sort of drawn to which set of identities? The Pythagorean. But if I look at the Pythagorean identities, they don't quite match up to this. I'm looking at the one that's got the sine squared in it and the cosine squared in it. But those were added, weren't they? Yeah. Is there some way that I could sort of rewrite what I'm looking at right now to fix that? You have to be really careful, right? This isn't an equation. Right? In an equation form, you can always multiply both sides of an equation and it doesn't change anything. And if I have just an expression and I just multiply it by -1, it will change my expression. But you're thinking along the right idea.
Sine squared is equal to 1 minus cosine squared.
Okay, so that's one thing I could do, right? And I'll suggest another option in a moment, but is it Tyra?
Yes.
Okay, so Tyra says I could leave the first part the same, and I could replace sine squared with...
No, the first part, 1 minus cosine
Okay.
squared is equal to...
So you're going to replace the first part.
Yes.
So we can do that too. 1 minus cosine squared is actually equal to sine squared. Right? If you look at that identity, sine squared plus cosine squared equals 1, and you subtracted the cosine squared to the other side, it would look like this piece of it, right? It certainly will. And if we replace that first piece then in that way, what is, oh, I put a theta when I did it over here instead of a 20. Sorry about that. So I've got sine squared of theta of 20 minus sine squared of 20, and again it's going to equal 0. The one other thing that you could do at this point right here, if you wanted to, you could factor a negative out. Okay, that's another option. So instead of sort of manipulating your equation or your identities, you could write this way. By factoring the negative out. And then it actually mirrors your identity that you have. Of course, either way you do it, you get the same answer, of course, right? It's still 0. Any questions on that one?